Okay, guys, can you hear me?
Yes, Professor.
Alrighty, how are we doing? Are there any, we haven't done this before, so any questions?
Do you mind explaining problem 2 from the homework? Like I got somewhere, but I'm not sure if it made any sense.
Okay. This is
Ibrahim.
Yep. Let's see. This is homework 5, is that correct? Yeah, so it's a little bit after tonight's lecture. I think you will have a better grasp of it. The thing that's a bit different here is that you're going to have, as you can see, the payoff of the option of the derivative. It depends upon both S as well as this A. So there are like two components in it. And so this is what we'll talk about as the second topic tonight. How do we deal with payoffs that potentially depend upon more than just the stock? Here, here it also depends on the sum, the accumulative stock price over time. So there are just a few changes, but yeah, we'll talk. We'll do an example tonight that is. It's not quite what you'll see in the homework here, but it's pretty close.
Also, is this an Asian type call because of the average of the total stock? Yeah. Okay.
So when we talk about Asians, this is typically derivatives that depend upon averages, or in this case, it just depends on the accumulative. But of course, you can divide in this expression here. You could divide outside by capital N if you so desired. Then it would depend upon the average stock price, right? The ones that we're going to be talking about tonight, those are called barriers, and they're not the same as Asians, but the underlying and the fundamental complication it comes because the payoff at the end depend upon other things than just the stock. Are there other questions or comments? So we'll postpone this discussion until a little bit later tonight, and because I think it's going to make a lot of the things that we'll talk about will help you get this problem too, right? Are there other questions here before we get started? Okay, then I say we get going. So again, if you haven't signed up for a slot on the for the midterms, go on Canvas, have a look under announcements, and there you can see the list of students that have signed up. If your name is on the list, check that it's in the right spot. If it's not in the right spot, let me know. If you haven't signed up, look at where the empty spots are, send me an email asking for a specific slot. We still have some time to get it scheduled, but of course, as we get closer, everybody needs to get a slot at some point. So it'll be easier if you somehow self-select, so I don't have to do it for you. But of course, if you don't do it, I'll have to do it. Okay. Let's do tonight's lecture. So there'll be two components to tonight. We're going to have a little recap of what we've been doing, and then we're going to do this extension where we're going to look at more general derivatives than just the ones that are written on the stock, right? So first the recap, and the recap is we're looking at derivative pricing. Right, so we're given a payoff function. I'm going to call it F capital N. It goes from R to R. This is a function from calculus. There's nothing random about this function. So now we're looking at a multi-period binomial model. And so we're out here at the end. There could be many more legs here. And so what is being predetermined, what is being given to you is this function here, fn of x. And so in derivative pricing, you know what you're given here at the end, like the payoff is going to be, this is the function, so the payoff is going to be fn composed with the stock at time n, right? So the payoff is going to be fn composed with Sn. So that's random. And it depends on what the stock price is. And so what you're interested in is moving this payoff backward in time, all the way up to time 0. You're interested in figuring out what is the value here at time 0. What is the price of getting Fn of x? So maybe I should write Fn of Sn of. Maybe I should write it Fn of Sn here. But we're interested in what is the value of a replicating portfolio at time 0 for getting this payoff here at the end. Okay, so the starting point is you move back iteratively. So you start by going from time capital N to time capital N minus 1. And so you're sitting here and you want to determine a function. You want to determine a function Fn minus 1 of Sn minus 1. Right, so what is the value of getting a payoff that's Fn of Sn one step later? What is the value of getting that one step earlier? And so provided that you can do that, you can then iteratively go all the way back to time 0, and then you'll have f0 of s0. So the question is, how do you go from one time point to another? So this is like a rollback. How do you roll back this payoff here? The payoff is given at the end. You want to figure out what is the value of this payoff at earlier times. Okay, so what you will do is you will replicate, right? You'll create a wealth process. So this will be your xn from n equals 0 to n. You create a wealth process such that x at the end is exactly going to be fn of Sn. Then the initial value, the initial wealth will be x0. This is the arbitrage-free price of the derivative. Okay, so what goes into creating a wealth process like that? So we did a long calculation last time. Last time we looked at the self-financing wealth dynamics. Right, so dynamics is about changes. So we have delta xn. If we have a self-financing portfolio, we'll compute what the changes are in it. This will be r xn minus 1 plus delta n minus 1 times, then you have this Sn minus 1 plus r Sn minus 1. This took a few slides, a few pieces of paper to calculate, and you can go back and check the slides from last time if you need to recall how to do it. I won't do it again. But you can see from this that if I am to create a wealth process, what I need to create is, so I need to find, or I should say create, I need to create the initial wealth, and then I need to create all these deltas, which is the investment in the stock. So I need to create this, delta 1, all the way up to the last one, delta n minus 1. This is for me to create a wealth process. What I need to do is to create the initial point and then create these deltas that go into how I get the changes in the wealth. Then I'll use this recursive formula, and this will give me how the wealth evolves over time. So the goal is to create these ones. The goal is to create all these elements such that at the end, I have the property that the wealth at the terminal time is exactly the payoff of the derivative. And so how do we do that? Well, we're going to explore a martingale property. We know that the discounted stock price, so this is also from last time, maybe from the time before. We proved that the stock price discounted so this is Sn divided by 1 plus r to the n. This is a p tilde martingale. And even further, even more was true, namely that the discounted wealth, this here was my xn tilde, is a martingale under this measure p tilde. So that's the property we're going to explore in order to do the creation of x0, delta 0, delta 1, all the way up to delta n minus 1. And so how will we do it? Well, if this is a martingale, right, this is a martingale, so that means that if I look at the conditional expectation, so under the tilde measure, so we put a tilde on top of the e, we'll have xn plus 1 with a tilde given fn. I'm going to get xn tilde. And then I can use the definition. This is the same thing, saying that the conditional expectation of xn plus 1 divided by 1 plus r to the n plus 1 given fn, that this is exactly going to be xn divided by 1 plus r to the n. So then what I can do is I can pull some of this 1 over r to the n outside and multiply through. So I'll get that xn plus 1 divided by 1 plus r conditional on fn. This is exactly xn. And this is my rollback operator. This is the thing that would ultimately be used to go from time capital N to time capital N minus 1 to time capital N minus 2 and so forth. For example, so we start, so we're going to start at the end. I'll use my formula. I'll start at the end, so I'll have that the conditional expectation x n divided by 1 plus r given f n minus 1. This is going to give me x n minus 1. But on the other hand, I know what I want this to be, because I want the replicating property. I know what I want xn to be. This is going to be fn of sn divided by 1 plus r given fn minus 1. So this is how we go from capital N, one step back to capital N minus 1. Okay, so here's the creation of the initial wealth and the deltas. So there are 2 steps. There's a 2-step procedure. So step 1, you want to create functions f0, f1, f2, and so on, all the way up to fn minus 1. Then step 2, so by using these functions, we will give formulas for the initial wealth and the trading strategy in the stock. Right, so the goal was to create the initial wealth and then the trading strategy in the stock. And the way that we're going to do it, we're going to create a bunch of functions, and then given these functions, we're going to give formulas for these quantities that we hunt. Okay, so how do we do it? So we're going to go on in step 1. Well, the first thing we're going to do is calculate this conditional expectation. So we're going to compute fn of sn divided by 1 plus r given fn minus 1. We're going to calculate what this is. This here is going to be, we'll use the binomial model. So in the binomial model, the stock price at a given time is equal to the previous stock price times the coin flip. and then condition. And then, so this is the definition. This is the definition of Sn in a binomial model. And the next one, this is going to be the independence lemma. That's going to be the next one. The independence lemma says that if you have a function of two independent random variables, one of them being measurable, you can compute this conditional expectation by taking the average over the independent component. So here we have Fn, and then you have Sn minus 1, and then psi can either be u or d. So we're going to take average over psi. So it's going to be u times p tilde divided by 1 plus r, plus it will be 1 minus p tilde times 1 plus r, Fn, and then it'll be Sn minus 1 times d. We've seen that calculation a few times before. And so this is going to allow me, we can then define so this is going to be my Fn minus 1 of x. This is going to be defined as this formula over here where I replace the random quantity by a dummy. So this will be 1 over 1 plus r p tilde Fn xu plus 1 minus p tilde Fn xd. So we were given Fn, and here we got Fn minus 1. By defining it this way, then we get that the conditional expectation Fn of Sn divided by 1 plus r given Fn minus 1, this is exactly Fn minus 1 of Sn. And so that's the key property, and this is really what we want. This is what we want to be xn minus 1. Right, this here is really going to be, this is what we're thinking about as being our wealth at time n minus 1. Did we all get this step here? This is how I create the next function. I started with the last one. Here I created the previous one. And of course you can iterate this. You can iterate. So you can get Fn x is going to be exactly this formula up here. 1 over 1 plus r, p tilde, and then the next one will be Fn plus 1 of xu plus 1 minus p tilde, Fn plus 1 xt. This here is how we create a bunch of functions. Fn minus 1, Fn minus 2, all the way down to 0.
So Professor, the equation, well, the formula you got after applying the independence lemma.
Yes.
What we did was we just made it more general in a way.
You're talking about this one here?
Yeah.
Well, here we replace the random quantity Sn minus 1 with a dummy. So here I call the dummy x. Right? Because I want functions here. I don't want random variables. Right? There's nothing random on the right-hand side here. So I got an expression here at the end, and I recognize that this expression here at the end, this is a function of Sn minus 1. Sn minus 1 is the only random component on the right-hand side. There's nothing else. Sn minus 1 is that's the only random component. P, R, U, and all these things, these are just constants. The only source of randomness on the right-hand side is Sn minus 1. So what I do is, I want to write this conditional expectation here as a function of that random variable. Okay, so what function is that? well, that function is going to be this fn minus 1 defined according to this formula. Does that make sense? Like,
I'm not complete. I mean, the way you replace the variable makes sense, but I'm not completely sure about the goal. Like, why did we know to?
So it's a two-step procedure, right?
Mm-hmm.
The goal is, and this is,
The goal is to create the set of functions.
right? The goal is to create these guys.
Right.
Okay, so I'm proposing a two-step procedure of doing that. First, we're going to create a bunch of functions, and then we're going to use these functions to get them.
Okay.
Right? I have not told you yet how to use these functions for anything useful, but presumably there is something useful to be done with these functions. It's not just, we're not just hanging out here for kicks and giggles, right? But I haven't given you the formulas for how do you use these functions to get to the goal. Okay, so that's step 2. However, before we do step 2, I want to make sure that we understood how did we get between the various equations in step number 1. Are we good on that? Right, so this function we have here, that satisfies that if I'm interested in computing the conditional expectation of fn applied to Sn, given if, maybe I should put a +1 here, given Fn, this is going to be f little n at Sn little n. Right, this is a random variable. Fn measurable, it has this property that it integrates correctly over subsets inside Fn. This is that function. So then step 2, is this useful? This is what Richard was asking about. And the answer is yes, this is really useful. It's going to do the trick. We have to come up with formulas for these guys. Any guesses on what x0 should be? What should x0 be? Any guesses on what delta 0 should be? So on. Well, this might not be completely crystal. This might not be obvious. But keep in mind, what is it that we are thinking? We are thinking that these functions here, as we move backward in the tree, they represent wealth at these different time points. So what should be the initial wealth? Well, it should be the thing that you have out in the root. Right, so the initial wealth should be this quantity here. Okay, so get this one. Now what about this one? And all the other ones? This is more difficult. This is not so obvious how one should get those, but we can figure it out. We can figure it out because the way that we're going to do it is the way that we're going to do this. We want the replicating property. So we want xn. This is my wealth at time n. I want this to be exactly fn of Sn. Like this is what that's why I wrote this in parentheses, right? I want this, the function applied to Sn minus 1. I want this is something that we want. So what I want is, I want this for n equal to 0, 1, 2, all the way up to time n. And so at time 0, we're good, because that's how we defined it. We go to time 0. So time 0 is okay. So we're going to try to get this to work for a generic time n.
So do we have to use the iterate thing that we just found out from before?
Yes. Yes. So we have it for time. We have a time for 0, right? So we have to prove it time 1, time 2, time 3, and so on. So pick a generic time. Let's call that generic time n. I want this property. So for a generic n, 1, 2, up to time n, we want xn to be this fn sn. And what I have to hang my hat on is I have a formula for the left-hand side, because we had this self-financing wealth dynamics wherever they were. I have them right here. Right, I can write this here out as this is equal to xn minus xn minus 1. So if you want, we can write this here as xn is equal to 1 plus r, xn minus 1, plus that other bit over there. Right, so I can take this expression on the right-hand side. Instead of xn, I take this expression on the right-hand side and plug it in here. So we want this to be true. I know what xn is equal to. Xn is equal to 1 plus r, xn minus 1, plus delta n minus 1 times Sn minus 1 plus r, Sn minus 1. And so I want this. And we've had equations like this many times before. If I'm sitting at time n minus 1, what is random here is Sn and Sn. So I'll have two possible values. If I'm sitting at time n minus 1, there are two possibilities for Sn. And so I really have two equations here. I'll get on one hand, it'll be 1 plus r. It'll be xn minus 1 plus delta n minus 1, Sn minus 1, and then it could be a u minus 1 plus r. This needs to be Sn minus 1 times u. And likewise, if I end up in a down state, I also want this to hold. So I'll put in the value of Sn in the down state. This will be d minus 1 plus r. We've seen these equations here, these two linear equations and two unknowns. We have two equations. It'll be xn minus 1, delta n minus 1. And we solve. Let me see if I can solve these equations without messing up. I'll get, what do I get? I'll move this term to the other side, I'll move this term to the other side, and equate them. So we'll get f n Sn minus 1 times u minus delta n minus 1, Sn minus 1, and it'll be u minus 1 plus r. This needs to be Like this term here is common, so do the other side, it'll be fn Sn minus 1 d minus this term. And then I'll solve, now I have one equation I got rid of the x's, so I have one equation in delta n minus 1. I can solve, and let's see what I get. I can solve, so I'll get 3 fn Sn minus 1 u minus this term, fn Sn minus 1 d. Can I do this in one go? I'll move this to the other side. I don't think I can do this in one go. It's going to be confusing. Delta n minus 1 is n minus 1, and then 1 plus r will cancel. I'll get u minus d. And then I'll divide over. I'll get that delta n minus 1 has a nice formula for it. U minus d downstairs. Upstairs is this quantity. Okay, so we managed to get a formula for the deltas. And the delta at time n minus 1 is involves the function fn. So that gave us a formula for delta n minus 1, but we also have an x here. We also have an x here. So what does xn equal? How do I get my xn's? I take this expression here and I put it into one of these two equations. And when I do that, I'll get something involving xn minus 1. So let me take the first equation. So we have 1 plus r, and I'll do the first equation. It doesn't matter which one you take, but let's do the first one. Plus, and then what do we have here? We have my delta n minus 1, this is this guy, times Sn minus 1, okay. So it's a mess, but let's see if we can get it to work. Downstairs, I'll have u minus d. Upstairs, I'll have this difference, fn Sn minus 1 u minus fn Sn minus 1 d. Okay.
So since we have a formula for n minus 1, right, would it work for finding out delta 0? Oh, I guess n would be 1 and then it'd be 0.
Yes. Right? Just pick n to be 1, and then you get f1 here. You get f1 here. You get s0 down here.
I see. Yeah.
But you see, if I do this thing, if we take n to be, if I take n to be 1, what should my x0 be here? That's going to come too, right? We have two equations, and if we're following Richard's suggestion and say, let's just pick n to be 1, I'm now going to be solving for x0 and delta 0, correct? What is x0?
F0, S0.
Mm-hmm. But it's also given as a solution to these two equations.
So it should match if you.
And what happens if it doesn't match? Any wild guesses? What happens if it doesn't match? Well, then
the answer is like there's arbitrage or something.
Yes, that's right. So now you can make your own exam questions, right? Say that you got down to here, say that you're trying to calculate and it doesn't match up. So either you did a mistake in the calculations, or the model you're working with has arbitrage in it. So here, the binomial model is arbitrage free, but you can see Rich has already preempted it, right? I know what I'm going to get here. There's no way around it, because when I put in n equal to 0, it has to be f0, f0. But how do we get that? Well, let's work it out. This is why we're doing this messy calculation here. So where did we get? We got to right about here, 1 plus r times xn minus 1, that was this guy. And then we had this term here, I got it from down here. And then we have u times u minus 1 plus r. And then on the right-hand side, this was fn of Sn minus 1 times u. Does it look like that this solution here is correct in the sense that it matches up with what it should be? Well, it's not still clear. Or maybe we can rewrite it somehow. Maybe we can rewrite it. Maybe we can move this stuff here to the other side. So we have that xn minus 1. I will have to have a factor of 1 over 1 plus r out here. Right, and then there'll be a term. There'll be something here with fn Sn minus 1 times u. Okay, I'll put maybe that outside. So here I'll have a 1. Okay, and then there's going to come a term here that's the same but with a minus sign. And then downstairs I'll have u minus d. Upstairs I'll have u minus 1 plus r. Okay, so that looks interesting. We will also have the other term. We also have the other term that has a minus sign here. Move to the other side, I'm going to get a plus sign. Fn Sn minus 1 times d. And then times a factor, u minus 1 plus r divided by u minus d. Is that something that looks familiar?
What looks like the adjusted, was it the discounted?
What is this quantity here? And what's this quantity here?
Oh, the probabilities, discounted probabilities.
Not discounted probabilities, right? The risk neutral probability.
Risk neutral, yeah. That's what.
This one here was 1 minus p tilde. And this one here was p tilde. So what do we have here? This is nothing else than 1 over r. I'll end up here with a conditional expectation of 1 plus r. It'll be fn of Sn. Condition on fn minus 1. Right, and this is by definition, this is equal to my fn minus 1 of Sn minus 1. Like that's how we created these functions. So it matches up. In particular, following Richard's comment, you put this to be 1, we're going to get that x0 is equal to f0 of s0. Right. So the solution that we got from solving these two equations up here is consistent. It is consistent. It's consistent with what we have here. So that's great. And so now we have all the formulas, right? We were able to provide the formulas that we need, so I can fill in, for example, what to put here. This is going to be S0 u minus d, S0 u minus d, F0 S0 u minus F0 S0 times d. And I can go all the way up. This here is my f n of Sn minus 1 u minus Fn Sn minus 1 d divided by Sn minus 1 u minus d. So I have all my formulas. And it works because I have this property. It works because I have this property that here that xn minus 1 is equal to this conditional expectation. In particular, for n equal to 1, this works, but it also works because where that slide was number 5. It also works, this one here, if I use this, this is to be true for all n between 1 and capital N, right? So when I take n to be capital N here, I'm going to get that xn is exactly equal to fn of Sn, right? Which is the derivatives payoff. So I have myself a wealth process that has the property that it ends up exactly where the derivatives payoff is. Okay, so then I'll just look at what the initial wealth is, and this is going to be my arbitrage price. Are there questions or comments on these first slides here of tonight? This is stuff that we have done. We've done it in examples. We've done it in. This is like what we've been working towards for a while, and okay, so that's how we create these recursive functions, and we use these recursive functions to define the wealth process. This wealth process has to have this property that at the end they give me the derivatives payoff, and then we can just look at what the initial wealth is, and this will give me the arbitrage-free price of that payoff. Then before we started here today, there was a question, namely, what happens when you have more general payoff structures than just what we had here? Let me just make sure I got all the questions. So is there any question about what we did in the first few slides?
Can you briefly recap the process?
Yeah, so there are 2 steps to it. So the way that I'm outlining it now is that it has 2 steps to it. First, you create a bunch of functions. And as one of you pointed out, when you create this bunch of functions, you seemingly don't have much to do with anything. But it turned out that you hold the key to creating this wealth process. Okay, so how do you create the functions? The way you create the functions is you roll back payoffs using this formula. You condition, you take the functions, so you know what they are at the end, right? Because fn is given as that's input, right? fn is given. So fn is given. How do you go from fn to fn minus 1? Well, the way that you do it is you compute a conditional expectation. Here, you're looking at the function at time n plus 1, composed with the stock price at time n plus 1, you condition, and that will bring you back to this function at time n. So that's step 1. Create these functions such that these expressions here you hold. Then step number 2, provide the formulas for the initial wealth and the replicating portfolio in terms of these functions. And so here we have the formulas. Now it's just a question, do they work? Well, the property that these that the initial wealth and these stock positions, the properties that they have is that at any given time, the wealth process has this property that is equal to the function composed with the stock. And that's the property you want, because if you roll this forward to time capital N, you're going to get the derivative payoff. And if you roll it back to time 0, you're going to get the initial wealth, right? And the initial wealth, this is that's what you're looking for in terms of the price of the derivative at time 0. So there are these 2 components to it.
Do you mind explaining step 2, the expectation of fn plus 1?
Step 2.
Right above step 2.
right above step 2. This one, but that's how we find the function. So we started out at the end, right? Because fn is what is given to you. So the first function you have to create is f capital N minus 1.
Okay.
F capital N minus 1, this is this guy. How do you find him? Well, you compute this conditional expectation. This conditional expectation, we did it on the previous slide. This was on slide 3 at the bottom. Right? We computed this conditional expectation, found this object here. What we want is to write this here as a function of Sn minus 1. Whatever this is seen as a function of Sn minus 1, that function we call Fn minus 1. Right, so that's this guy here. And then we just continue doing that. So now you have Fn minus 1. So now you want to get Fn minus 2. So then you compute the conditional expectation. Instead of n here, you have n minus 1, you have n minus 2, and so on. And, so at a generic time, you go backward from Fn plus 1, composed with the stock price at time n plus 1, condition on an earlier time, and that's how we find the function of n.
Okay, thank you.
Yep. So that being said, there was a question in your homework that asked for something that is more general. So in the homework, it's being asked for a more general structure. So we're going to ease into that now. Sometimes some derivatives, they have payoffs that depend on more randomness than just Sn. So barriers, so examples include barriers. Barriers are like maximum and minimum. So if I do, which one is it I want to do today? I want to do the maximum. So the maximum will be take the maximum stock price up to time n. Another example is what you had in your homework, Asians. Then you'll need to look at the sum, say from k equals 0 to n of the stock price. Barriers, we think about barriers, again. The option knocks in or knocks out if the stock price has reached a certain level over its lifetime. And so then you have to keep track of the max or the min. Asians, they typically pay out something depending upon the average stock price, right? So then you have to keep track of something like this. Maybe you'll have to keep track of maybe it's n plus 1 here. You have to keep track of something like this.
Do we add Sn n plus 1? Oh, okay. That's good. Yeah.
Okay, so and then you get payoffs. So before you'll have a payoff, which will be this would be Fn that would go from R to R, and the payoff would be Fn composed with Sn. So more general, it could be a payoff. So I'm going to be focusing this is now today, and this here is in the homework. So we'll have a payoff, but now we'll be two-dimensional. So we'll go from R squared into R, you'll have the form fn, sn, and then I'll have my m in here. So now there will be two quantities in there. So how do we do it? Well, the key step is, so the starting point would be write, that's how it always is. You always have to write the random quantities in terms of something that is measurable with respect to the previous time point and something that is independent with respect to the previous time point, right? So we start, so as before you write the stock price, Sn, you can write this as Sn minus 1 times your coin flip, right? And it has the property that Sn minus 1, this is Fn minus 1 measurable, and the coin flip is independent. Right, so this is what is needed to use the independence lemma. So we're good there. But now we also have this m sitting in here. We have this m sitting in here, so we need to deal with that. So how do we write m? So m here in the following slides will be this maximum. I need to be able to write the maximum in a similar way as I wrote the stock price, namely as something that is measurable and then something else which is independent. Now, how would I do that? Well, it's the maximum. So I want to write it in terms of something that was measurable with respect to the previous time step, right? So I can write this here as the maximum at time n minus 1. Okay, so what else do I need to do to it? I want to get the maximum at time n. How do I get from the maximum at time n minus 1 to the maximum at time n?
Take the max of Sn and m n minus 1 and Sn, yeah.
Right, and then I plug in what I had before, right? So this is going to be the maximum m n minus 1, and then instead of Sn here, I'll plug in this formula. So now it should be in good shape. This should be all that is needed to do the we did before. So two-step procedure. Create step 1. Create these functions f0, but now of two variables, right? f1 up to fn minus 1. And how do we do it? We need to have a conditional expectation of my payoff. This is my fn. That's the thing that's given to us. We're given the function. We're given the function. Plug in the random quantities. So this here would be Sn, Mn, condition on previous time point. And then we take these formulas we had for the random quantities and plug them in here instead. Fn, then we have Sn minus 1 times the coin flip. M here is this maximum thing. M n minus 1, Sn minus 1, and then your psi, given n minus 1. Now we use the independence lemma. We use the independence lemma to perform the calculation. What we need to do is take average. So we have this is measurable, this is measurable, this is measurable, with respect to n minus 1. Xi n and psi n, it's the same psi n, of course, is going to be independent of what happened up to and including time n minus 1. So we take the average. This will be p tilde fn applied to Sn minus 1. Now here this will be a u. That'll be the first entry. Then the second entry will be a maximum. Then we have Fn n minus 1 is n minus 1 times u. That was the probability of it being heads when we get to u, and then we also have to have 1 minus p tilde Fn, and then everything similar except for u being replaced by d. It's a lot of writing, but it's not conceptually. It should not be so tricky. We use the independence lemma. What you do is you take the average over the independent component. So what I have here will now be my function. Right? I want to write this as Fn minus 1 evaluated at Sn minus 1, Mn minus 1. I probably need to discount, so we have a discount factor out here too, 1 over 1 plus r, 1 over 1 plus r, 1 divided by 1 plus r, so 1 over 1 plus r. So I want to write this as a function of Sn minus 1 and Mn minus 1. Okay, so how do I do that? So we're going to define Fn minus 1 at, we call it x, and then we call this for m. Two dummies, it'll be 1 over 1 plus r p tilde Fn. And then instead of Sn minus 1, we put an x, we put a u, put a max, put an m, put x, u. That was the first part. And the second, 1 minus p tilde, Fn x d now, and then we put the max, m x d. That was how we created the second to last function. We performed a conditional expectation calculation, and the functions get more and more messy, but now it's two-dimensional, so we have both x and m here. X is here, m is there, x is there. And of course, this carries over to more generally. You'll get f of n of xm. This will be 1 over 1 plus r, and then just replace Fn here will be Fn plus 1, one step later. And then the max. So this gives us all the functions that we had from before. And now, given these functions, how do we create the replicating portfolio? Well, the initial value is going to be f0, and then you get the replicating portfolio. It's going to be exactly as what we have here. What happens is that we move up in dimension. So step number 2 here is similar. This is similar to before. I would rather spend the last few minutes talking about what is going on. And so we're moving up in dimension. We're moving up from just looking at payoffs that depend upon the stock payoffs that depend upon more things. Right, so the technical term here, this is what is called a Markov. This is called a Markov process. And math finance folks calls this these for state processes. So you'll see the word state processes many places. Probabilists call them for Markov processes. And so the thing to note is, so we note that if I compute a conditional expectation, you can either put a tilde here or put a p here. It doesn't matter much for what we're doing right now. If I take a function of, say, Sn plus 1 condition on Fn, we've been able to compute what this here is. We've been able to write this here as a function, say, g of Sn. Right, so for any f, we found a g such that this is true. And similar, we even did more. And similarly, we just did an Sn plus 1, and then we had an Mn plus 1 condition on Fn. We were able to write this as a function of Sn and Mn. What about if I did a function of Mn plus 1? What should that be equal to? Is this here a function of Mn? Is this here true?
Well, Mn plus 1, are we doing this max thing again with it?
M is always the max. M is always the max.
No, I mean like when we break it up into like it's the max of Mn and then like the Sn.
So, but before we find the solution, I always like to have the intuition first. But it makes it a lot easier if we can somehow build up this intuition. So we have an idea about, do we think something like this is true, or do we think something like this is not true? Like we check this one, that's true. We check this one, that's true. What about this one? We don't know. Do we have an opinion about it? So you're suggesting how to figure it out, but I would like to have like a little step in between that says, okay, so what do we think? Is this going to be true? And Timon, he says, no way, this doesn't work. And this is correct. Yeah. So the answer is no. Okay, and so now how do we get to Timon's answer? Well, we do what Richard suggests. We break up this this Mn as before. We write this as a function of, and then it'll be M. And then we need to take the max. Oh, I should have written this a little bit bigger, huh? Let me try to write this a little bit bigger. E of f, and then I need the max, Mn, and then Sn, my psi n plus 1, as before, given Fn. And then I'll work out what this is. I'll use the independence lemma as before. Take out what's known. What's known is Mn and Sn. And then I'll take the average over what's independent. So this will be P tilde F max Mn Sn. And then this here is now a U plus 1 minus P tilde. And now F max Mn Sn. And now this is a D. So is this a function just of Mn? And what Timon is saying is that this is not true, right? Because you need both Mn and Sn. This is not just a function of Mn.
To go from that last step, was that just a definition of the expected value, or was there an independence lemma there?
It's always the independence lemma.
It's okay. It's always
right? Because this quantity here is independent of that one. This quantity here and this quantity here, these two, they're measurable.
right. Okay.
Right, so I'll have here that Mn and Sn, they are Fn measurable. And I'll have that psi n plus 1 is independent of Fn. So the answer is no. Okay, so this here leads to this, not leads. What we're looking at here is more general. The thing that we're looking at here, this is the Markov property, right? So this is the definition. A stochastic process let me write it as Yn. This is a Markov process. You can also say that it is Markovian if you give me any function g, I can find, no, any function f, I can find a g such that the expectation of f applied to yn plus 1 given fn is simply just g of yn. Right, and y could be, this is just a note, yn could be multidimensional. What do I mean by multidimensional? For example, we would have that yn is equal to this stock and this running max. Or, as in your homework, yn could be the stock and then the aggregate stock. So what we saw in the example was that Sn is Markov. We saw that Sn, and we saw when we combine it with M, this is Markov. And we saw that Mn by itself is not Markov. Any questions or comments on this? Just want to direct your attention a little bit to one of the homeworks. If we go and have a look at the next homework, where did it go? Here. This is the next homework. So we again playing with basically what we did in today's class was solve the first problem, but what I really wanted to show you was that I put a few optional problems on because we're falling behind. So this was supposed to be part of the homework, but now it's optional. I gave you a bunch of processes here, 2, 3, up to 7. And it's asking you to single out which ones are Markov, which ones are not Markov. When you go up in dimension, sometimes you can, if your answer is no, then maybe you can try to add more processes such that it becomes Markov. Like in the latter part, the example is that the maximum by itself was not Markov, but if you included the stock price, Sn, Mn, that would be Markov. And so here is an example. Here are examples where you can try to practice and try to figure out a more general structure than what we just had on the previous slides. And that's what this optional problem here is about. It's about practicing on how to recognize what processes are Markov and which processes are not Markov. It's optional, so you play with it if you feel so. Otherwise, it's okay. The first question, this is what we did in class. I want to make sure you guys internalized it. Are there any questions or comments? Maybe I can ask the student who had the first question before we started today. Did that help a little bit on the understanding of the homework?
Yes, it did. Thank you.
Yeah, I figured that it might. Otherwise, if it's still not clear, then on Thursday we have another chance, and then we'll have office hours both in the morning on Thursday, and we have the lecture on Thursday, so we can try to clear up there.
Okay, I'll try to finish it. Thank you.
Are there other questions or comments? Okay, so where we are now in the textbook is we were playing here with these macro processes. This is in section 44. Right, so we're done here with the first few parts. Next time we're going to be talking about these Ramanujan derivative processes. Right, so this is coming in here, and we actually also need a bit from the second book. There's something called, well, I'm sure you guys have heard about base rule. There's a couple of results over here in section 5 in the thicker book that we're going to be talking about next time. And another thing we're going to be doing is, even though I'm sure that everybody has heard about base rule, I put up just a few problems on the base rule that you've probably seen a number of times in your undergraduate course. I'm putting it up because we're in this pandemic right now, and I find it very timely to discuss base rule because a main application of base rule is about testing. And if you go to the doctor and you get tested for COVID-19, your doctor, he will know what base rule is. I know, I asked my doctor, and he know what base rule is. And if you read something like problem 4 here, you can see there are like these numbers that report accuracy of these tests. But the question that you really want to know is, if your test is coming back positive, what is the actual probability of you being sick? What is the probability of you being sick given that your test is positive, even though your test is 90% accurate? Does that mean that you are sick with 90% probability? And that's the part that I want to make crystal clear in these examples, that to answer that question, you need to know Bayes' rule. Because the answer is not, even though that the test is 90% accurate, the probability of you being sick, even though your test is positive, is not 90%. It is a far cry from 90%. In this particular example we're looking at here, it's 8%. So if you're not used to playing with Bayes' rule in this dimension, I want to spend some time talking about that next time. In particular, during a pandemic like this one, where every day you open a newspaper or you look online, you will find discussions about how important it is to have these tests be so and so accurate. And I agree with this, but I would also very much like to know what the probability is of being sick given that my test is positive. Like, a specific example is my kid's school yesterday. The first patient in that school was tested positive. Right. So a natural question to ask is, what is the probability that this patient that tested positive is then actually sick? That would be something that I would like to know. And so to answer that question, we need to know Bayes' rule. So I put in a few problems here about Bayes' rule. I hope you guys want to have a look at it. It's very timely given what we're going through right now. That being said, we'll start with this next time. Then we'll go into talking about random evidence processes and so on. And I'll put a few problems about that on here too, just for good measure. So there are like 5 problems related to that too in the end. But we'll talk about this next time. Yeah, we have a few minutes left. Are there any more questions or comments about tonight's lecture?
Yeah, Professor, I saw, I've seen this Markov process described before as like when you condition on multiple points in time, only the most recent one matters.
Yes.
Is that equivalent to like what we wrote before?
But that is what we're getting, right? We're getting this multidimensional setting. That is exactly what is happening, right? Fn has the entire history of y in it, but only the most recent one matters.
Oh, I see. Okay, so Fn is right. Fn is the segment algebra, the small segment algebra that contains all of the
yes
y1 to okay. Yeah. Got it.
Other questions, comments? Okay, then I bid you all a good night. And if you haven't signed up, send me an email about a preferred time slot for the midterm. Otherwise, I'll see you guys on Thursday morning for office hours. Good night, guys.